Welcome back everyone to 1.5. In this video we're going to be evaluating infinite limits numerically, right? So our main goal, calculate out some infinite limits and detect vertical asymptotes. So the claim is you've probably encountered vertical asymptotes before, and you may have seen them in something like y equals 1 over x, or y equals tangent of theta, or something like this. So let's do a little bit of a review on where we've seen these things before, and then we're going to, of course, build on this. So, okay, explore y equals tangent of theta. This isn't a lot of information here, of course, but we can go ahead and maybe draw. The first time we probably saw a tangent was in some sort of triangle, right? So I'm going to go ahead and draw a triangle here. And triangles, probably the first time you saw these were in right triangles. So I'm going to draw a nice right triangle. You have some angle theta here. And the claim is that tangent was equal to the opposite over the adjacent legs, right? So sometimes, right, if I was to do tangent of theta equals y over 1, you could say the opposite maybe could be y, and adjacent could be 1. So here's an example of a triangle, right, where tangent of theta is equal to y. And now, if you let this theta value grow a little bit, right? So grow, maybe get closer and closer to like 90 degrees. Now I'm going to really ruin the rest of my text. But as this theta value gets closer to 90 degrees, or pi over 2 radians, this y value is growing, right? This is getting larger and larger. So as theta approaches 90 degrees, or pi over 2, which is probably what I would prefer, then tangent of theta, or in our case y, will approach, well, it's getting very, very, very large, so it approaches positive infinity. So this is one of the first times that you can come across a vertical asymptote. Okay. So in this class, right, we're going to view these things more from a limit standpoint, right, since we've been practicing our limits. So let's first of all do a little bit of review here. The line x equals a is called a vertical asymptote of the curve y equals f of x if at least one of the following is true. You don't need all of them by any means, just one of them has to be true. So the first thing that could happen is that as you approach a, right, as x approaches a from the right, f of x is equal to infinity, right? So it's going off to positive infinity. So maybe our function looks something like this. There we go. And then as it gets closer to a from the right, it goes towards positive infinity. So here would be an example of our function in which that is true. However, it could also be as you approach from the left, it's equal to positive infinity. So maybe I'm going to draw an even more different function this time, something like this. But then as we approach from the left, our function goes off towards positive infinity. So here would be a case of that. Or better yet, maybe the two-sided limit, right? So in both cases, they both approach positive infinity. So from the left and from the right, we're both approaching positive infinity. If any of these are true, then we say the function has a vertical asymptote at a. But not only positive infinity, right? We could also do all the same sort of thing with negative infinity. And here are some graphs to go along with that. All right, so you may want to, of course, pause the video and you can sketch these all down, but I hope you have the idea. So more precisely, right, this means that f can be made arbitrarily large or small in the case with negative infinity. So when I say small, I don't mean close to 0, I mean quite negative, right? So negative 100 million, for instance, by taking x to be sufficiently close to the value a, but of course limits, we don't let them be equal to a. Close, but not equal. Okay. So how do we find them? Right? That's what this remark right here is for. How do we find vertical asymptotes? Well, for functions where we have a numerator and a denominator, the claim is if the numerator is not equal to 0 and the denominator is equal to 0, then we're probably going to get a vertical asymptote, especially in this class, right? So to verify, we should compute left and right hand limits as x approaches a. So let's go ahead and practice here with example 510. Find the vertical asymptotes for the function And you can see we have a nice fraction here. We have a numerator and a denominator. Usually the way that I start these things is that I take the denominator. Remember the denominator here, we want the denominator to be equal to 0. So I'm going to try to figure out the places where it's equal to 0. And those are going to be my potential a values. So okay, what does it take for the denominator to be equal to 0? And okay, usually the way that we solve these is by factoring. So I'm going to factor out an x. And okay, so that means we have two numbers multiplying together to give out 0. So we have either x is equal to 0 or x is equal to -1. And a common mistake that I see is that people just leave this as is, right? And they maybe highlight this and there's your answer, right? But there's two conditions, right? You need the denominator to be equal to 0 and the numerator should not be equal to 0 at that value. So these give me kind of potential a values. So 0 and -1 are potential a values. But what happens, right, if I go ahead and I plug these into the numerator? So for instance, if I plugged in 0 into the numerator, so here, plugging into the numerator, if I plug in 0, I get 0 squared plus 0 plus 1, that's equal to 1. That is indeed not equal to 0, so this one passes the test. X equals 0 is indeed going to be a vertical asymptote. How about -1? If I plug in -1, I'm going to have, let's see, -1 squared will be 1. Plus 2 times -1 plus 1. And so when I simplify this down, I get out 0. So because I got 0 in the numerator, this one does not pass the test, right? Maybe I should do this in like red or something like that. So this one does not pass the test. So in fact, the only answer here is when x is equal to 0. This is where we're going to get a vertical asymptote. And in fact, I'm going to skip it for just a second here, but we're going to verify this down here in 512. We're actually going to compute the limit as x approaches 0 from the left for this thing to verify that we actually get a vertical asymptote. Okay, moreover, let me show you another way that we can kind of look at this, is that if you were to fully simplify this down, fully simplifying this down usually gets rid of the things that are not vertical asymptotes. So if I was to factor not only the denominator, right? If I factor the denominator, I get this. But if I factor the numerator, right, if I factor the numerator, this is going to be x plus 1 times x plus 1. Notice that the x plus 1's cancel out, and you only have an x in the denominator remaining, right? So that corresponds to x equaling 0 being a vertical asymptote, but that x plus 1 factor canceled out, right, with the x plus 1 in the top. That's why x equaling -1 was not a vertical asymptote. All right, now let's move on. The claim is, well, this one is going to have a vertical asymptote, right? So if you try plugging in 1 into this function, you're going to have 5 on top. Let me just go ahead and maybe freehand this for a second. 5 on top. If I plugged in 1, I would have 0 on bottom. So this is going to be a vertical asymptote. But the question then becomes, is it going towards positive infinity or negative infinity, right? And so that's the question that we're trying to answer right now. We want to evaluate this limit. So we're approaching 1, but we're approaching 1 from the right-hand side. And there are a couple different ways to actually kind of reason through these. But I like to imagine, right, if I'm approaching from the right-hand side, I'm plugging in something a little bit bigger than 1. I'm plugging in something like 1.1 or 1.01 or 1.001, right? Something that's bigger than 1. So if you take any of these, right, and you take 1 and you subtract away, so if I take 1 and I subtract away 1.1, or if I take 1 and I subtract away 1.01, or if I take 1 and I subtract away 1.001, the claim is in all three of these cases, we get a negative number. So that this, I will actually write out -0.1. This is equal to -0.01, -0.001. All three cases you get a negative number. So when you plug in something that's bigger than 1, and you subtract that away from 1, you always get a negative. So sometimes the notation that I see is that you see something like 0, but a little bit less than 0, right? It's technically like a -0, right, for whatever that means. So you have a positive and you divide it by a negative. A positive divided by a negative, this is going to give you a negative. So in fact, the answer is negative infinity. So for these types of problems, I quite often get asked, what kind of work are we expected to show? And unfortunately, there is not a lot of work. It's a lot of reasoning, but there's not a lot of formal work that you have to show for these types of problems. Quite often I see them maybe as multiple choice problems, things like that. But, here's the answer, negative infinity. Let me try to convince you really quick that this is indeed the case, and I'm going to cheat here for a second and pull out my calculator, right? I know you don't get a calculator. But, just for the purposes of understanding, let's go ahead and pull out our calculator here. All right, so if I take 5 and I divide it by, let's do parentheses, 1 minus, and I'm going to do 1.1, right, something like that. And I hit equals, we get negative 50. If I do the same thing, entry here, and do 0, 1, plug that in, we get negative 500. So it does seem the closer that we're getting to 1, seems to be getting more and more negative. Right? Or you could say smaller and smaller, I would guess, yes, negative 5,000. So the closer that you get to 1 from the right, the more and more negative you get. And this comes down to when you divide by 0, right? Dividing by 0 is the scary thing that we're not really allowed to do. When you divide by 0, you're going to be getting either negative infinity or positive infinity, and it really depends on, is that 0 a little bit negative or a little bit positive? Okay, let's upgrade then. This is a more complicated problem, right? It's a tougher function. We're going to be approaching 0 from the left. We already saw up here that we think 0 is going to be a vertical asymptote, so we're expecting to get either the answer negative infinity or positive infinity, but let's see what we get in this case. All right, so as we saw up above, we can actually simplify this function, and I really recommend anytime you can simplify the function, do. So we're approaching 0 from the left, and again, this is x plus 1 times x plus 1 divided by x times x plus 1, and so we get a bit of cancellation. And so the true question becomes the limit as x approaches 0 from the left of x plus 1 divided by x. Okay, so now let's go ahead and pretend really quick here. If I was to just plug in 0 everywhere I saw an x, I would have a 1 on top, and I would have 0 on bottom. Now, because we are approaching from the left, right, we're technically smaller than 0, what do you think? Is this 0 going to be positive or negative? Well, it's probably going to be negative because, again, x itself is smaller than 0. So again, we get 1 divided by negative 0 to some extent, right? A very, very small number, very close to 0, right, but just a little bit negative. So in this case, again, the answer will be negative infinity. Now I want to show you, sometimes people get confused, right, and they see, anytime you approach from the left, you see that negative sign and they think, they try to say that this is always going to be negative infinity. That's not necessarily the case, right, because up here we approach from the right. So by that logic, this should be positive infinity, but indeed the answer was negative infinity. So you really do have to think out each one of these problems. All right, that is the end of Section 5. I'll see you guys next time, Section 6.